This video, we're going to be going over intramolecular forces, VSEPR, shape, polarity. Now, that last video, we went over intermolecular forces, and that is the forces between molecules. So if I have a hydrogen bond between water molecules, that would that would be an intermolecular force. This, though, is an intramolecular force. It happens in between the atoms of the molecule themselves. So it happens inside the molecule. All right, so we have different types of chemical bonds. Ionic would be where your electrons are transferred from the metal, which becomes the cation, which is positively charged, to the anion, or to the nonmetal, which becomes the anion, which is negative. And there's an electrostatic attraction. So they're attracted to each other because they are unlike charges. The other type would be covalent, where electrons are shared between nonmetals. Nonmetals want to gain electrons, so they will share electrons if they're going to bond together. Now, metallic bonds, that's where you have different metal atoms bonded together, and the electrons are shared between all of the metal atoms. So it's not just between two atoms, it's between a group of atoms. And then when we look at certain compounds, what we'll actually see is that they have both ionic and covalent character. So some covalent compounds actually exhibit some ionic character, which gives them different properties. Maybe they are stronger, maybe they make brittle compounds, or they'll have some sort of ionic property to it. So whenever you have a question and it's asking how come this compound exhibits this property, it's probably because it has some ionic character to it, or some covalent character if it's an ionic bond. Okay, so when we're looking at an ionic bond, we have cations, which are positive, and anions, which are negative, are held together in this crystal lattice structure. So when I have this crystal lattice structure, I have an arrangement of positive and negative ions. So the positive ions will be surrounded by the negative ions. So the positive ions will always be smaller ones, the negative ones will be larger. And basically they just kind of arrange themselves in this crystal lattice, which is a very ordered structure. And you'll have the positive ions around the negative and then vice versa. So basically they will distance themselves away to maximize the attraction and then minimize the repulsion. So you've got these positive charges and you don't want those next to each other, so they want to be far away, but we're going to put the ions in order so that we can maximize the attraction between these two and minimize the repulsion between these. Now, they're still going to have the same ratio dictated in your formula. So if we have magnesium chloride, I should have 2 Cls for every 1 Mg. It's just all of them together will make this arranged, ordered structure called the crystal lattice. Now, Coulomb's law basically predicts that the attraction of the ions are going to be greater if the charges are greater and then if the ions are smaller, because if you're smaller, you can get closer to each other. So if we're looking at these two compounds right here, which one will have a stronger attraction? So magnesium oxide or calcium oxide? Well, this is +2, this is -2, this is +2, this is -2. Okay, so the charges are the same. So what we really need to do is we need to look at the size. Well, oxygen's in both of them, so we can look at the size of magnesium and calcium. Well, calcium is lower on the periodic table, which means that this is bigger. So since this is bigger, these atoms, these ions, can't get as close to each other as these. So MgO will have a stronger attraction, and because of that, they will have, I don't know, higher boiling points, higher melting points, things like that. So they have more of an attraction, which means that they're harder to pull apart. Okay, let's look at another one. Okay, let's look at LF or Li H2O. Well, let's look at the charges. We have +1 and -1, and I have +1 and then also -2. Oh, +1 and -2. All right, this one actually has a greater charge, so this one should be stronger. So right here, since I've got a stronger charge, it's -2 instead of -1, this one will lead to stronger ionic bonds, which will lead to higher melting points and so on. So I could also have something like magnesium oxide versus sodium chloride. Well, if I look at the charges, I've got magnesium, which is +2, oxygen, which is -2, and then +1 and -1. Well, this one would have stronger ionic bonds because it's got ions which have higher charges. They're more attracted to each other. All right, so because of that crystal lattice structure and the electrostatic attraction that we have, it leads to different properties. So ionic compounds typically have high melting points and high boiling points, low vapor pressures. They are brittle, so if the layers happen to slide so that the negative is touching the negative, then they suddenly break apart. So if I'm looking at this right here, this is my normal crystal lattice. Well, if something happens and the layers slide so that the positive is right next to the positive, negative right next to the negative, they break apart. That's why that you have this property. So ionic compounds are brittle. Now they can conduct electricity, but only if they're in a liquid state, because the ions need to be able to move. So if it's in the solid state, the ions can't move, so we can't conduct electricity. They need to move. They can also dissolve in water because those polar water molecules are very attracted to these ions. It's called hydration. So if I take an ionic compound and I put it into water, even the insoluble compounds do dissolve to some extent. But if I put a soluble compound into water, these water molecules are attracted to these charges and they pull them out into the solution. And they solvate them, they surround them with the water molecules. All right, so a metallic bond is when we have multiple atoms, and basically we have all of these atoms are sharing electrons. So we actually have some positive charges, and then these electrons are just kind of moving all amongst the atoms. So it's called an electron sea, or really it's delocalized electrons because they're moving amongst all the atoms. Because we have the structure, it leads to ductility, which means I can stretch it into wire, malleability, which means I can bend it, thermal, and so they are electrically conductive and also will conduct heat very well because of the structure. So the greater the number of electrons, the stronger the metallic bond is. Now, when we are looking at metals, sometimes we make a mixture of metals to give us different properties in those metals. So technically, if you have gold, gold is actually a very soft metal, so they will add other ingredients to the gold to make it stronger. There's a couple of different types of alloys. One is called an interstitial alloy, and that's where we put small atoms to fill the spaces in between those large metal atoms. And basically this makes it more rigid and less malleable. So if I add carbon to iron, and carbon is significantly smaller than iron, it's going to make it stronger, and that's actually called steel. So a substitutional alloy, well, it substitutes for some of the atoms. So we take an atom of a very similar size and we replace it in that alloy. And this makes it less malleable. So copper and zinc would make brass, and then this would be an example of a substitutional alloy. All right, so whenever we make a covalent bond, basically those atoms are they're coming closer and closer together because they're attracted to each other. The electrons are being attracted by the nucleus of the other atom, and they're coming together. Well, as they come closer and closer, those nuclei actually get close and they start to repel each other. So the distance that the atoms end up being in the bond is the bond length, and that distance will create the lowest amount of potential energy. So basically, it's going to stabilize the bond. It's going to minimize the repulsion that the nuclei feel from each other, and then also maximize the attraction of the electrons that are being shared. So that distance that we minimize that potential energy, that's the bond length. And then the potential energy that they sit at when they're at this length is actually the bond strength. So when we have a covalent bond, it can either be polar or nonpolar, and really that's based on the difference in electronegativity. So the higher the difference, the more polar the bond. The electronegativity is the ability of the atom to pull electrons towards itself when it bonds. So if it's able to pull the electrons more towards itself, it ends up creating this negative end and a partial positive end on the other side of the bond. So it's an unequal sharing of electrons because one is more electronegative. It pulls the electrons closer to it. Now a nonpolar bond, there's a very small difference in electronegativity, if any, and there's an equal sharing of the electrons. So nonpolar bonds usually happen with the same atoms. So if I have Cl2, it also happens between a CH bond. These are not polar at all. So these atoms will share the electrons equally. So if you look at your periodic table, the more distance they have in between themselves on the periodic table, the higher the difference in the electronegativity. And remember, the most electronegative atoms are going to be right around fluorine. Fluorine is the most electronegative. Okay, so Lewis structures. So if you are really rusty with this, I suggest you go back under Unit 3 and look at those videos. But I'm just going to go over a few examples of drawing Lewis structures. So carbon dioxide, first thing I'm going to do, I'm going to count how many electrons I have available for bonding, which are the valence electrons. So if I look at carbon, carbon's in group 4, so it has 4 electrons available. And if I look at oxygen, it has 6 because it's in group 6, and there's 2 of those, so that's 12. So 12 plus the 4 would give me 16 total. So I have to place these 16 electrons around these 3 atoms. Well, carbon will go in the center. It's the only singular atom here. The least electronegative one usually goes in the center, and then oxygen around it. Okay, so so the next part, all right, so when I'm looking at this, I know that these are the valence electrons that are available. Okay, so now I need to know how many electrons does each one need to have. So most atoms want to have 8 electrons to complete that S and P sublevel, except for groups 1, 2, and 3. So carbon wants to have 8, oxygen wants to have 8, and there's 2 of those. So that's going to give me 16 plus another 8. So 24 electrons. So it wants to have 24 electrons. So what I can do with this is I can actually figure out how many bonds I'm going to make in this without even trying to draw it first. So this is one way you can help double check some of your Lewis structures. So 24 minus 16 would be 8 electrons that are being shared. So 8 electrons are being shared. Well, each bond will represent 2 electrons, so it's going to be 4 bonds. And also, carbon will always make 4 bonds. So you need to make sure that carbon, whenever you have it in your structure, has 4 bonds. So we have 1, 2, and we need to make 2 more bonds, so 3, 4. So oxygen typically likes to have 2 bonds, carbon likes to have 4, and that's what we have right now. All right, so that's only 8 of the electrons, so 2, 4, 6, 8. Now I need to place the rest of them. So 2, 4, 6, 8. Now I move to the next atom. 2, 4, 6, 8. So now this has 8, this has 8, this has 8. That's good, and I've used all my 16 electrons. All right, so let's look at another one. Let's look at carbonate. Okay, so carbonate has a -2 charge. So let me count how many electrons I have available. Carbon has 4. Oxygen has 6. There's 3 of those, so that's going to be 18. And I've also got a -2 charge, which means I have 2 more on top of that. So I've got a total of 24 electrons. Well, if I want to figure out how many bonds, let's see how many everything wants to have. Everything here wants to have 8. I've got 4 atoms. So that's 32. Well, 32 minus 24 will also be 8 electrons. So each bond is 2, so I need 4 bonds. All right, well, carbon will go in the center. Oxygen, oxygen, oxygen. All right, so I need 4 bonds. 1, 2, 3. Well, it's 3. I need to get an additional bond. So it can go here. It could also go here or here. So now I need to finish placing the rest of my electrons. So 2, 4, 6, 8. So that one's satisfied. Let's move to the next. 2, 4, 6, 8. So now I move to the next. 2, 4, 6, 8. All right, so now at that point, it is satisfied, carbon satisfied, and I have used all of my 24 electrons. So again, if you don't remember how to do this at all, I would definitely go back and look at those Unit 3 videos. All right, so valence bond theory. Basically, bonds are formed by the overlap of atomic orbitals. So 1 electron from each of the bonded atoms is going to be used in that bond. Both electrons in that overlap, so the electrons that are being shared, are going to be attracted to the nucleus of the atom. And then we have 2 different types of bonds. We have sigma bonds, and sigma bonds happen when the electrons are being shared directly between 2 nuclei. Okay, so here's my nucleus here, and here's my nucleus here. So if they're going to be shared, they're going to be shared right here. So it happens when we have an s orbital and another s orbital come into contact, and they share those electrons directly between 2 nuclei. It could also happen in between 2 p sublevels. So p sublevels look like this. So my electrons here will be shared between the 2 nuclei. Basically, a sigma bond is when we're sharing electrons directly between the 2 nuclei, and that can happen with an overlap of the s orbitals or an overlap of the p orbitals. Now, a pi bond happens when the electrons are not being shared directly between the nuclei. So a pi bond would be like this. So we have our p orbitals, and here's my nuclei right here. Here are my nuclei. So we have these 2 p sublevels, and basically when they bond, the electrons are going to be shared like this. So they'll be shared here and here. And the nuclei are right here. So they're not being shared directly between the 2 nuclei. So sigma bonds are stronger because they're closer to those nuclei. And pi bonds are weaker because they're not going to be shared directly in between those 2 positive charges. So when we talk about bond strength, sigma bonds are much stronger because they're directly in between those 2 positive charges. Now, a single bond is just 1 sigma bond. A double bond is a sigma bond and one pi bond. And then a triple bond will happen when we've got one sigma bond and two pi bonds. And this is just the way that they will arrange themselves so that we can continue to share those electrons. So we have multiple bonds, double bonds and triple bonds, and they are stronger and also shorter than single bonds, but they're not 2 times or 3 times as strong. So a double bond is not twice as strong as a single bond because a pi bond is weaker than a sigma bond. And a triple bond is not 3 times as strong as a single bond because pi bonds are not as strong. So because we have these overlapping orbitals, we actually have something called hybrid orbitals. So basically, because the p sublevels and the s sublevels come into contact and we are blending those, we create a hybrid orbital. So it's blending the s, the p, and the d orbitals. So only sigma bonds can be hybridized. Pi bonds cannot be hybridized. So you can determine the hybridization by just counting how many lone pairs each atom has, and also the number of sigma bonds, not pi bonds, on the central atom. So basically, if you have two sigma bonds, it would be one s and one p, because you're blending an s orbital, which is 1, and then you're blending it with a p orbital. So that'll be 2 orbitals that you're blending. If you have 3 pairs, it's going to be sp2. So I'm blending one s with 2 p sublevels, so 3 pairs. And then if I have 4, it would be one s orbital blending with 3 p orbitals. All right, so let's look at a few examples. Okay, so CH4 would look like this. So methane. So what we're going to do is we're going to count around the carbon, and let's determine the hybridization. So we're going to count how many sigma bonds I have. Well, it has 1, 2, 3, 4 single bonds, and a single bond is equal to 1 sigma. Well, it has 4 sigma bonds. So 4 bonds means I'm blending 4 orbitals. So it's always going to be just one s. So I have s, and then I have 3 more orbitals, so 3 p orbitals. So that's 1 s and 3 p, which is 4 bonds. All right, let's look at C2H4. Well, this is going to be a carbon chain. And then I'm going to put my H's around it. Carbon likes to have 4 bonds, remember, so 1, 2. Well, I've run out of hydrogen, so 3, 4. It's got a double bond. All right, so now let's look at the carbon here. I'm going to count how many sigma bonds I have. And remember, a single bond is a sigma bond, but a double would have a sigma and a pi. But remember, pi bonds do not hybridize. So I have 1, 2, 3, because this is just one sigma bond. So I have 3 bonds. So I'm going to count. That means I'm going to have 3 orbitals, so 1 s, and then I need 2 more, so 2p, so sp2. All right, and then water. All right, so I'm going to count. So I have 1, 2 sigma bonds, and I also have 2 lone pairs, so I have to count those too. So 1, 2, 3, 4. I have 4 bonds. I need somewhere to put these lone electrons. So again, that will be sp3. All right, so resonance happens when more than one Lewis structure is possible. So usually you're going to see this when a double bond can be placed in more than one spot. So if you have resonance, the bond length and the bond strength is actually going to be an average of the single and the double bonds, or if you have a triple bond in there somewhere too. So carbonate has resonance. I can put the double bond here, here, or here. And because of that, my bond length is not going to be that of, I have 2 single bonds, so the length of CO single bond and then length of a CO double bond, it's not going to work that way. It will be an average between something between a double and a single bond. So it's not going to be as long as a single or as short as a double. It'll be somewhere in between that. All right, so formal charge is used in two different ways. It's used to show where the charges might lie in the molecule, and it's also used to show what the most possible resonance structure is. Basically, you want to make sure your formal charges are as low as possible, that they add up to the overall charge, and that the more electronegative atoms have the negative formal charge. So to get formal charge, you're going to take the number of valence electrons and subtract the number of non-bonding electrons plus 1/2, I think that should be 1/2 the number of bonds. All right, so let's look at carbonate. Okay, so we're going to count the formal charge on each of these atoms. And remember, it should be -2. All right, so all the formal charges on this molecule should add up to -2. So let's calculate the formal charge around this oxygen right here. All right, so the number of valence electrons, well, oxygen is in group 6, so it has 6. And then we're going to subtract the number of non-bonding electrons, which is, let's see, 2, 4, 6. So 6 non-bonding electrons plus the number of bonds. Oops, sorry. So right here I should have 7 and 6 minus 7, which would be -1. So this one is going to be -1, which means this one will be the same thing. All right, so let's look at the one with a double bond. All right, so we've got 6 valence electrons. I'm going to subtract how many non-bonding electrons, so 2, 4, plus the number of bonds, which would be 2. So that's going to be 6 minus 6, which is just 0. So I have a 0 charge here, and then let's do carbon. So carbon has 4 valence electrons, and then it has 1, 2, 3, 4 bonds, and 0 lone electrons, so that one would also be 0. So let's make sure that it adds up to the charge. So -1 plus 0 plus -1 plus 0 should be -2, and it is. All right, so I'm going to ask that if you're going to look up your shapes, you can refer to your VESPR reference sheet. Now, when we're talking about polar shapes versus nonpolar shapes, polar molecules have an asymmetrical shape. And when we say that it has an asymmetrical shape, that means the dipoles do not cancel. So, if you're reading a multiple choice question or answering an FRQ, it's not because of the asymmetrical shape, it's because when we have this asymmetrical shape, the dipoles do not cancel each other. So most shapes with lone pairs on the central atom will push the atoms closer together, and it makes an asymmetrical shape. So that creates, those lone pairs push the atoms closer together because those non-bonding electrons repel more strongly. So if I have NH3 like this, ammonia actually, I'm going to have a lone pair, and that actually pushes these atoms closer together than they normally would be, and it creates dipoles that don't end up canceling. So if we have a lone pair on the central atom, it's usually going to be polar, and also if you have an atom that's attached to different atoms, the dipoles won't cancel. So if I had like this, carbon bonded to 2 chlorines and then 2 hydrogens, the dipoles won't end up canceling each other because this magnitude will not cancel this one, or this one won't cancel this one. So if it's bonded to different atoms like this one, or if it has a lone pair, it's usually polar. All right, so let's look at the shape of this one. Okay, so I have one lone pair. Okay, I have one lone pair, and then I have 1, 2, 3 bonding pairs. You count a double bond as one thing. So 3 bonding. Well, 3 would be trigonal, but because I've got that loner pair right there, it actually pushes them closer together. So it's not going to sit in a flat plane like it normally would. It's actually going to push these atoms closer together, and it's going to be trigonal pyramidal. And if you do not remember any of these shapes, I definitely suggest you go through and at least memorize the most basic ones, like tetrahedral, trigonal pyramidal, trigonal planar, because that will be something they can test you on. All right, so let's look at carbon dioxide. Okay, so carbon is in the middle. So when I count, I'm not going to count double bonds as 2, I'm going to count it as 1, because basically you're counting how many atoms are bonding to the central atom. So I have 1, 2. So I have just 2 bonding, 0 lone. So basically it's going to sit as far away from each other, the oxygen atoms will sit as far away from each other as possible, which will lead to a linear shape. And those atoms will be 180 degrees away from each other, because that's the degree of a straight line. Some covalent compounds actually create something called a network. So this happens when we have atoms that just bond together and they just make this one huge structure. So group 4A atoms are very good for this. So carbon, silicon, these elements can lead to these structures. And because they're this huge network, it actually leads to high melting points and very hard solids. So these network structures actually create a lot more strength. Okay, so in these network substances, you can have a 3-dimensional shape and you can also have a 2-dimensional network. So the 3-dimensional one can be found with diamonds. So these carbon atoms actually sit there and they start bonding to each other and they actually create this kind of structure down here. So these are sp3 hybridized, and it leads to very, very strong bonds, and then that leads to high melting points and high boiling points. Silicon can do this as well, but silicon can actually conduct electricity. Carbon cannot conduct electricity. Now, if we were to take carbon, though, and put it into a 2-dimensional shape, like graphite, these sheets are actually stacked in layers. And because there ends up being free electrons because of the sp2 hybridization, they can actually conduct electricity. So graphite, the stuff that you find in your pencils, can conduct electricity. Okay, so network solids are very, very strong, but you can also have a molecular solid structure which isn't quite as strong. Basically, molecular solids, so if you have a covalent compound that is a solid, they're held together, those molecules are going to be held together by intermolecular forces. So it makes them weaker than the network structures where you've actually got these covalent bonds in between so many different atoms. But they still are stronger than other covalent compounds, like water. So in these molecular solids, electrons are not going to be free moving, so they're non-conductors. So something like solid iodine would be an example of that.